you can repeat again.
Yeah, I will take. Look, here. So here, yeah, you see each time your capacitor. Yeah, I sent you. Yeah, your capacitor is in the circuit. Yeah, and you have like here. Imagine that it's not present here, and imagine that it's 1 and 1. If it's 1 and 1, then the second is here and here. Yeah, imagine it's 1, 1, 2, 2. If 1 is opened and 2 closed, oh no, it doesn't work. It's not a good example. But imagine we don't have that, and they are opened. What? The plates of this are not connected to this, are not connected to this, so they are connected to anything. Yeah.
This line, last line, or last line, or fourth line.
Line.
Table. Round, fourth round table. Up table.
Yeah.
At this case.
Yeah. In this case, in the homeworks, yeah, it was the fourth one.
Four,
because here it's a ground, you know?
No.
So in the homeworks, it was like that because we had like ground. Hi, German guy, German tourist. They are grounded, but imagine we don't have anything here. When we close the capacitor, we like it's not connected so it's this line. I don't know if I'm really clear, but plates are not connected to internal nodes, and that's just why that. How are you? Fine. Good. Good.
Yeah.
Good. Yeah. Cool.
Nice. Very good.
Yes, okay.
Just the question of the key. Yeah. Brilliant. You have you had 2 interviews?
No, I had more.
You had a lot of interviews and 2 said yes, and now you can decide.
Some other, yeah. Oh,
And
but the second
what are the two?
one is just I sent my cover letter and also my cover letter and my CV. Sorry. And yeah, so I sent him to the director of the company. Maintenance of it.
Nice. Then you didn't even have an interview, they were just like, yeah.
Yeah.
And which companies are they? Do you already know which one you're going to choose?
Yeah. It's called RAG Defense.
RAG Defense?
Yeah, you know?
I've
you
heard of it,
RAG, it's really present in Germany.
yeah. I think I've heard of it, yeah.
You know? Okay.
I don't know,
Okay.
specifically.
But in France, they have a filial in Switzerland and France.
Yeah. You want to go into defense?
Yeah. What do you
I don't know.
because it's not your choice, right?
Yeah.
I'm not.
Defense? I'm not sure. Building weapons. I'm not sure if I want to build weapons.
Yeah, but you know, in our current role, to have kids also. It's, yeah.
I think that would be a long second company that
It was just a consulting company. I went it.
in consulting there's some money.
Yeah, no. Is it the same consulting company and how do you say it? Consulting and service company, like you a group of engineers and company calls them when they need something to design, for example, the system.
Yeah.
It's a consulting company.
Yeah, it's like
Yeah.
consulting.
They have money, but yeah.
And you might potentially do a lot of like very different things.
What?
That's also interesting. So you have like the option to do like
Yeah.
a lot of very different.
But you know, it's a little company, and I'm afraid that it will close a lot of doors. If I begin with that, I'm afraid that later I couldn't do something else. You see what I mean?
That you're. Though also sometimes little companies give you a lot more like, you know, they're more flexible, you have more freedom to move through the company and like
but
see
my
different
problem
things
is
and get
it's
like
really
experience.
next to Paris. I don't really
Want to,
I
okay,
want
yeah.
to, and also you know, yeah, I lived there since I'm 14.
And you wanna get away from Paris.
Yeah, really.
Yeah.
And also,
Yeah,
you
makes
know,
sense.
for renting it's really expensive. Yeah, you have a lot of friends, but I don't like the life in Paris because
Yeah.
like people are always running, and also to see friends, you see them in 2 hours and after they have to go somewhere else, etc. And also to
Yeah.
and here it's in the south of France, next to Toulouse, do you know?
Yeah.
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 I told you.
I would like. I mean, I know very little about sometimes, but I think I would like Atlantic coast. I would like the Atlantic coast.
You would like to?
I think I would like the Atlantic coast.
Coast, yeah. Bordeaux.
Yeah.
Yeah.
Like something
Let's
to the
look
west.
where is it? I want to
West
look.
of North.
I'm so happy.
Yeah, nice, super, yes. I know the feeling. It makes me really happy. It's
It will
amazing.
well, also south is where my family lives.
Mm-hmm.
Paris is here,
Mm-hmm.
and you have Toulouse here, and it's just here.
Yeah.
So we make this next week. Okay?
Can I-
Yeah, sure.
It's called
Albi.
Albi.
Today.
Yeah, it looks like a nice area and lots of like mountains.
Yeah, sure.
Yeah.
I think I want to find somewhere to work and also to live in a good way, like in a good mood, to meet people, etc. And you see, like Toulouse is really big, Montauventoux, it's south, and
Yeah.
northern Atlantic coast.
Yeah. But I haven't really been there. Oh, there's a national park here. That's always good. Having like a big network.
We had a second house in New York.
So let's start. So today we will talk about some practical aspects. We will consider how to simulate the switch capacitor circuit. So look, just now I would like to say that you should be near the finish of the low pass filter design, and of course we will start so today's lesson from the questions that you can ask me about the possible problems if we are talking about the low pass, about some maybe additions or something like that. But mainly I would like to demonstrate you some specific concerning the use of microcap. You see, for your understanding, the question is that it is the typical program. It is the typical package, and all other things more or less the same. More or less the same from the functionality point of view. So, and the moment is that switch capacitor filter, or maybe we can say circuit, it is a so-called parametric circuit because its structure depends on the clock frequency, clock period. And this is the reason that, generally speaking, the possibilities of the microcap is not oriented to the analysis or simulation of a such type filters. It means that we need some additional extensions how to use the specific of the microcap and maybe any another packages for the solution. And this is the reason that I would like to demonstrate you one of our approaches. We have used it here, and it is very effective. So look, first of all, some examples. This is the previous. This is the results obtained by the previous. Yeah, maybe.
Thank you.
Yeah, this is one of the structure. And just now we will see how it is. So, this is the filter, for example, or something like that. More or less you will have similar structure. Switches, operational amplifiers and capacitor. The question is how to realize this block. So look, we cannot simulate it on the frequency domain. For example, if we are talking about the filter design and consider the analog continuous time circuit, it is possible to use this approach. So in other words, after the simulation of the frequency domain, we will have the amplitude response. Something like that. You have seen it many times on the prototype. The question is, we couldn't use the same approach for the parametric circuit. It is possible to simulate it only on the time domain. Only on the time domain, you see? So, and the formulation of the task. How to use the time domain simulation if we would like to obtain the amplitude response. So look, classically, amplitude response can be realized on the frequency domain, but we cannot. So it means that it is necessary to think how to do. So, and we will start from the presentation of the final results. So look, here it is possible to see. It is the spectrum of the input signal. And you see, we have, yeah, and this is the frequency, of course.
It's V out.
Yeah, this is the output and this is the input. So look, here is the frequency and this is the spectrum. And you can see that it is uniform. Now, for example, it is 100 millivolts or something like that. It doesn't matter. And there is no changing of it on this frequency range. It is stabilized. But if the signal come into the input of the filter, it will be filtering. So it means that the output signal will not be equal to that. So look, this is the output. First of all, it is possible to see that it is Chebyshev. So look, there is some changing of the cover of it. And here we have more or less the passband, and here we have the stop band. You see, the spectrum lines will be low, 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 and of course here will be very small. So, and you see, the idea is that we can simulate the circuit on the time domain, and after that we can transform the obtained results into the frequency domain if we use FFT, fast Fourier transform. You see the idea? And just now the question is how to realize this comb input source. Comb input source. Generally speaking, it is a specific term, comb. I mean, do you know it? So look, C-O-M-B.
Okay, I don't know.
Yeah, but it is, how to say, just a minute, for your understanding. It's like interpreter. So look, comb, and it is the instrument like that. For the hair.
Pen. Okay, yeah, okay.
You see, and exactly,
sure.
and
Right,
exactly
I
we
didn't
have
know the word.
exactly here we have more or less the same situation. And this is the reason that normally we can say that it is the comb source on the input, input excitation. You see, and the question is how to realize the things. So let's see. Let's see, where is it? Anywhere. Yeah, this one. So look. And it is the combination. It is the combination of any of the harmonic, we can say harmonic sources. It is a harmonic generator. And each of them has their own frequency. And it is exactly corresponds, yeah, coming back to the input. This is the in. This is the frequency. Each frequency corresponds to each of them. You see? And after all, it will be possible to combine the results into the one summer here, step by step. And here we have the signal like that. It is the kind of combination of all of these things. The question is, which kind of element, or we can say component, can be used for that? It is an important thing, not this one. So look, it is a so-called voltage controlled voltage source. Voltage controlled voltage source. Controlled voltage, it is here. And this is its output. And if we have the coefficient of this block equal to 1, it means that here we have, for example, the sum of these two. And the same situation here. It is the sum of this.
Okay.
It is the sum of this. And so on for all of them. You see? To this, to this, to this, to this, to this. Say other words, we have the line of summator. After all, it will be also possible to summate the signal from this summator, you see? For example, here, for example, here, for example, here, and for example, here. And after all, we also can combine using the next summator, the results of this, the results of this, and after all summate it here.
Yeah.
Okay.
Well, this is an idea. And the output, we have the total combination.
Yeah. And the frequency from which to which and the step amount.
It depends on you.
Depends
It depends on you. Of course, it is necessary to think of it.
Yeah.
You see, and but some practical
Just to have a
recommendations.
good representation of what
Exactly,
we expect.
because we have the ripple.
Yeah.
We have the ripple. It means that we have specific points, maximum, minimum, and of course, you should have the step to understand where is it to compare with the prototype, to understand that it is correct and so on. And this is so the kind of possibilities for to understand which kind of frequency step we need.
Yeah.
No, so but of course it is
Yeah.
necessary to see how it is and to use something. But so this is a good approach. This is a good approach. Okay.
And that is in order to have a comb. Yeah. Okay. For the input.
Yes, of course. Yes, for the input. Yeah. So, say other words, what we have as the result. As the result. Oops, let's see. So this is the calculation of the elements, and after all, we will see. That's what we need. We need the input realization. Of course, we need the structure of the filter. No, more precisely, more better. It is the same, it is, but the scale is small. It is difficult to understand which values of the capacitor here, and this is the resistance. Here we can see all things, you see. With the elements, with the values. But it is a kind of modification. The next, of course, it is the clock. Control voltages. First phase, second phase. With all parameters, you see the time period, so time voltages, and specification. Combination, input, output, and the scale. That's more or less to understand which kind of losses we have here. Attenuation. So look. So this is a good result, and it is decibel.
Yeah.
And this is characteristic point, because in accordance with the specification, we have the technical requirement for exactly for this frequency points. This is the cutoff, and this is the stop. Stop frequency, and it is possible to see that it is exactly corresponds to the specification.
Yeah.
So and here the passband. So look, the question exactly about your question, which time step? You see the cover corresponds exactly to the prototype. It is quite good. You can compare with the previous, so on the before.
Yeah.
So you can see Chebyshev. It's good.
Okay.
This is only passband. Yes, it is only passband. You see with the very small ripples. So look. This ripple, the low pass filter. So, and it is in the time domain. A very specific illustration, you see, because it is rather difficult to understand what we have here. It is only for your understanding that really we have the results on the frequency domain. We should understand what kind of spectrum we have and so on. Here also, of course, it is a kind of difficult signal, no more. And we have this one. After all, FFT, fast Fourier transform, and we will have this one. And so on. But on the time domain, of course, it will be the kind of it is not possible to understand what's that, of course.
Why is it discrete here?
Yeah, because of the switching. You see, switching, it is the kind of, it is the operation of the spectrum shift. And it is exactly like here, because we will have the portion of the frequency parts in, how to say, on the scale, on the frequency scale, which is proportional into the main frequency. So the part on the main frequency, the next one with the index 2, the next one with the index 3, and so we will have something like that. And this is the reason that the whole signal will be the kind of combination of it. But of course it is also the question of scale, because normally so we have the same signal. This is the same. Yeah. So something like that, something like that. And just now, yes, please take your seat. It's so interesting. By the way, so very interesting guy. This one. The guy there were two students, but they were from Iran, from Tehran. And just now, both of them are working in the Ministry of Science and Technology of Iran, and with a very good qualification, and they are looking good. Now, you see, it is important for us because we should understand the comparison with another scientific school, from another university, what we need to obtain our higher level and how to compare the results of our studying process with another one.
Yeah.
Yeah, and from this point of view, it is the kind of successive stories.
Can I see something?
Hmm?
Can I see something? Just
Yeah.
a little bit.
I give for myself the,
Ah.
the special mark here to
I,
for do not forget
Okay.
about it.
they are from?
From iron.
I
Yes, Tehran.
I understand Ireland. Okay.
Tehran.
Yeah, just okay. Yeah. Because I was like it's really big and
But it
it's
depends
because
on,
they,
you see,
they what,
yeah, the question is that they have a strong interest on the topic, and it was for them. Yeah, why? The reason is very simple. Simple because in their own university they have seen a kind of general theory concerning the selective circuits, concerning the filters, but this topic for them will be totally new. So it was the reason that they have read another book, additional book, I mean, about this, and put a lot of things, calculations for the report.
Yeah, okay.
For them it was important, and it was the kind of main project for them during the master.
Yeah.
This is the reason. Of
Same
course, it
mistake.
is not necessary. It depends on you should be. Generally speaking, that yes, sufficient to have 20-25 pages, no more. So look, half of them will be your figures,
Yeah.
yeah, the calculations.
Okay.
Not too much.
Okay, so yeah, it's because the okay. Okay. So we are with this. So. And yeah, for with no, it's okay. Thank you.
So, well, what we need to finalize this part of the work. So, first of all, it is necessary to see the catalog of the integrators here. And just now I would like to demonstrate you a very simple example how we can use this catalog and which kind of integrators can be used practically. For this reason we will take the simplest, really simplest prototype of the second order. It's really the simplest circuit, and we'll see how it is implemented using the switch capacitor approach. You will use the same approach for your circuit, but of course the order will be higher in your case. So for example, the cover will be fifths, Chebyshev sevenths, and so on. No, but for example, use Chebyshev and you can fix the order. Okay, how to do it? So let's see some illustrations. Yeah, of course, this is the approach we have considered altogether concerning the operational simulation method. Say otherwise, it is integrators with the feedbacks. You remember. So you use the same. The simplest example will be based on the structure like that. It is the prototype, second order prototype. R and C. We will use the approach we have considered. The first element, this one, Y, the second element, Z. The first element is like here, S here. Usually we use S for the complex frequency. Yes, S. SL, the second number is C, and it is necessary to use some additional transformation concerning the normalization and so on. So T1 is equal to Rn R, SL, it is equal to R, S, L, Rn. Normalization parameter, we have talked about it. The second one, T2, it is SC, CRN. So, and it should be with the sign minus. So, the realization. If we are talking about the prototype, so from here, what we have the element like that. The first one. This is the realization of T1. This is the realization of the T1. Yeah, put it here, T1. Realization for the second, it is the classical Miller integrator. So it means that we have like here, and the feedback, and for the first block, with the strich, here is T2, with the strich, it is equal to -1, T1 with 2 strich will be equal to -R0 plus PCR. Oh, sorry, once again. S. S. So, and T2 is equal to minus SCR. So, totally T1 and T2. No, so it will be multiplication of this. So, well, what we have? Coming back to the switch capacitor. What we have? It is necessary to realize the transfer function like here and the transfer function like here. The first one corresponds to the first order low pass filter without inverting, with the sign plus. The second corresponds to the integrator with the sign minus. So, you see the catalog, and we have a number of transfer functions. It is possible to use it. So let's see what we have. The first block.
When you talk about the catalog of transfer functions, it's...
Yeah, it should be here. Now open it. This is the next paragraph with the active elements, yes, after the simulation. Yes. Also look, the number of integrators and the transfer functions is here. It is possible to analyze each one of these blocks. The results are here. And you see that we have a number of inverters, we have a number of non-inverters, and all of these things are integrators.
okay.
Yes, non-inverting, inverting, and so on. You see, from this point of view, the switch capacitor technique is more universe. Because just now, see, it will be possible to realize this structure with only 2 operational amplifiers instead of 3 for the analog circuit. You see, and we will see how it is. So, the first. This is the realization, just now we are talking about the realization of the first transfer function, of this one. So what we have, the structure will be like here. Oh, no, maybe just a moment. I think it will be better to reserve some. Some places for the here. So this is the realization of the first transfer function, T1. T1. And we need only one operational amplifier. And the question is how to do the phase for these elements. And the second block which corresponds to the transfer function T2. So what we have here, this is the output, and we need the last block, feedback, this one, feedback, this is a T2. Of course, in your case, you will have the same approach, but for the more difficult structure. But nevertheless, it will be more or less the same. The next block will correspond to the inductor, the next to the capacitor, the next to the inductor, to the capacitor, and so on. Yeah. So the total structure will be approximately like this,
Just-
but with a number of feedbacks.
It's just because it's bigger. that's-
Yes.
Yeah.
The order is high.
Yeah.
The order of the circuit is high. So this is the reason. But anyway, just now we can compare switch capacitor and the envelope. You see, there is big deal. Yeah. By the way, concerning this, concerning the phase, first, second, and so on. Once again, come here. You see the results, and it is possible to see which the sign we have here, plus or minus. And in accordance with this specification, it is possible to use this phase or this phase. Because we understand which sign is here. T1 is plus, T2 is minus, and so on. And vice versa. The next T3 will be with plus. So because it's changing. Plus, minus, plus, minus, plus, minus. So, more or less that's all. My proposal is to finalize next week the low pass filter and to demonstrate something from you.
Okay.
And we will start the last part concerning the cascade design, as I said. So we will see some specific and some basics concerning this approach to understand how to realize the band pass filters. It is an important from this point of view. And by the way, look, just now we have considered these things. This is an example, you see. T1, T2, the feedback, and the structure. Okay.
It's here. Ah, yeah, okay. Ah, yeah, exactly.
Now you will see.
So
the next week, my proposal is to use the computer from your side, for example, or maybe you have a flash. It is possible to use the computer class if necessary. But if you have the laptop with you, of course, we will do it here.
It would be necessary for me because
You said about the Linux. Yes, we will go here and so prepare something concerning it.
So we should do this for our structure.
Yes, I think
yeah.
yes, to demonstrate where are you now.
Okay.
Yeah, how it works. Do you have some problems or something like that? Because we are near the finish. And
Okay, great.
Mhm. But I would like to say that it is very practically oriented. I think just now we have the knowledge which can be considered as a kind of combination of the theoretic basics and practical skills,
Yeah.
because after the finish you will understand how it works totally. And you see, maybe from the practical point of view, maybe only the last step which we do not have the possibility to realize because we are limited in the time. You will use here in your design the idealized switches from the library. Of course, from the practical point of view, it is necessary to use MOS transistor for this realization. And if we are talking about the simplest one transistor circuit, of course, it is only the changing of each switch by the transistor. But practically, it is more difficult circuit. It is possible to see it in the literature. That is well known. But of course, it is a little bit more difficult. But I think just now you will have the basics to understand how to do it, and it is
Yes.
the main task for us.
What is the which non-ideal property about a MOS transistor
Yeah,
is
you see,
the core problem? Is it the resistance or is it the speed?
both capacitors, parasitic capacitors, and resistance. Yeah, and you see, the problem is that there is some specific effects that should be eliminated, and these effects because of the parasitic capacitors from the gate to the circuit. Remind that. So this is the switch, and the simplest circuit is realized like here. And you should remember that here on the gate we have the clock frequency, the clock signal will be here. And there is the parasitic capacitor from this point of view and from this point of view. So it means that the clock voltages will go directly to the circuit. And it is very bad effect because it is the kind of additional noise. And just now, of course, we have the spatial realization of the switches, which is based on 6 transistors, and it is the known circuit, and it is the possible to use the principle of pre-distortion. So in other words, if we understand how to combine all of these transistors, 3 of N-type, 3 of P-type, and to combine it to the one block, it will be this combinational switch. There will be there will be on the output node the combination of positive and negative effects. So in other words, there will be the voltages with the sign plus, and from this side there will be the voltages with the sign minus, and they will eliminate each other. And the question is only how to calculate N-type and P-type elements, and it is possible to do it.
Yeah.
And this practical recommendations we know, and you see, the problem is only one. The question is that parameters of the N transistor and of the P transistor are not the same.
Yeah.
And we have some changing of it, and it is necessary to combine only this. But it is on the little. Yeah. Maybe this is only the last moment, and unfortunately we do not have the time. But I think it is understandable for you because just now we have a good experience in all stages.
Yeah.
Prototyping, active prototyping, and the final real circuit. No, so?
Okay.
Yeah, and the last moment for today. The last moment for today also practical. I mean the analysis of the integrator on the Z domain. Did you see something? analysis of the integrator. Sorry. In the Z domain, I mean Laker model approach we have considered.
Yeah.
Did you see something?
Yeah.
Okay. This is a training for you, and of course, yes, please do it, because
Yeah.
on the exam we will see the task line.
And just me, I have the question.
Yes,
We
please.
are supposed to know that, or like because I used the
So
table.
look, the question is that this is the general result.
Yeah, and this is.
And this is the
special-
particular cases, some specifics. So look, not for example,
Mhm.
what's the difference between the line 1 and the 2?
It's grounded.
Only, yes, right, of course, only this node is grounded, and that's all. It means that you know where is this node on the general figure. It is
Ah.
possible to ground it and to obtain the
Ah,
particular case. So it means that first of all you should understand how to do this one,
Mhm.
and after all another things will be the particular case
Okay.
of this.
Ah, yeah, yeah.
Possibly only one node will be grounded, maybe 2 nodes will be grounded, of course, for these cases.
Mhm.
And of course you should understand which one.
Mhm.
But of course it is theoretical basics, you should understand how to realize it. And of course these cases where we do not have the connections with the
Yeah. Okay. Yeah.
From this point of view, once again, it is necessary to understand how to do this one, and all another things will be considered as the particular case of this.
Mhm. Yes. Yeah, it's okay.
And you will do it, of course, as a training, as I said, you so ground the node here also,
Mhm.
and you see that you will have this figure.
Mhm. And also, yes, direction. Yeah, also plates.
Right, of course, yes. Yeah. It is necessary to keep in mind that the charge can be to this side or to this side, and we have to,
Yes.
to use it.
Mhm. And at the end, when we do that, just we have the matrix reduction. It's
Mhm.
linked with the amplifier, and we erase the lines and columns.
Yeah, in accordance with
yeah,
it.
yeah.
Yes,
Yes,
right.
yeah.
Mm-hmm.
It's just the I did it, but I lost the reason why we do that. Just linked with the amplifier.
Yes, because of the virtual ground rule.
Ah, yes, it's yeah.
Yes, we believe that we have the ideal amplifier.
So
It
epsilon
means
is equal to 0. Okay. Yeah.
yes to the 0.
Yeah. Okay.
Yeah.
Yeah. Okay. Yeah.
This is the reason.
Thank you.
It is called virtual ground rule.
Virtual.
Virtual ground rule. Yeah.
Okay. Thank you.
And so, how is your things? Is it okay?
Okay.
Mm-hmm.
Up to now.
Mm-hmm. No, so let's see if you have any questions also. Yes,
Yes.
ask about it if necessary. And so that's all for today, thank you.
Okay.
Mm-hmm.
How does this follow from that?
Sorry.
How does this follow from that? That's
Plates.
yeah, if the plates are not connected, then you.
It's not connected here, so we don't have that on that. So we will erase all we have. Yes, between with K and L. So this.
So look,
Yeah.
the idea is
Adjust.
so look.
You
This
add
node
them
On
together.
the second case, this node is grounded. This one.
Mm-hmm. Yeah.
It means that here on this figure we should see where is this node.
Yeah, no, I understood
this-
all of them, but I didn't
Ah,
know what
this
this
one.
one yet.
So same,
Yeah,
Oh,
with
yeah,
the-
that
and
is the
I
same.
just need to like wrap my
It is
mind
so
around
yeah, I
it.
see. So this is a simple thing. You can analyze this structure. Only this one. You see, the question is that here we have the kind of combination where there will not be connection with the internal nodes. It means that for the combination of this element we can use the same rules as for the standard classical analog components. To summarize it, yeah. So, for example, if we have two admittance, it is possible to sum it. If we have two resistors, it is possible to sum it.
So we just sum this and this and this and this, and then we
Something like
have
that.
them in parallel.
Something like that. But to understand this figure, of course, this is the simplest case. Here will be more difficult. You can see this one, it is sufficient. You can use not this, but this, of course. Sorry, with this one.
Yeah.
No, where the elements both are grounded, you see. Yeah. But the question is that on the second phase, there will not be additional elements to this node because of this.
Yes.
From the practical point of view, what does it mean? It means that on this switched element, we have only one key.
Yeah.
For example, only on the one phase, like here, and there is no any connections on the second phase. By the way, from the physical point of view, it is understandable why here we have z minus 1 instead of z minus half. You see, because the discharge is obtained only on the one phase. Here it is stabilized and there is no any changing of the charge of the capacitor on the second phase and only on the first. And the first phase will go once again after the total period. The total period delay corresponds to minus 1 instead of minus half.
Okay, yeah.
So the conclusion. It is necessary to see this case when it will be possible to combine these elements. Here on this node we have external elements in accordance with this one.
Yes.
But for this part we do not have. It is possible to edit each to other to summarize and to see how it will be. And you will see that after all we have this structure.
Okay. Okay, I need to do the
From
ones.
this to this.
Yeah.
And of course from this to this. And it is totally understand. You will totally understand these effects.
Okay.
But anyway, if you have, you can take your calculations with
Yeah.
yourself and we will see how it is.
Yeah. I just need to do it once for myself.
Yes, by yourself, exactly,
Yeah.
exactly. Yes, yes. Take the papers and we'll see how it is.
Yeah. My girlfriend is waiting downstairs, so
No.
I better be with her.
Okay.
Goodbye, picture.
Bye.
I love short lessons. I love short lessons.
You have it like
Knowledge.
yeah.
I will get it punish it for the pages. And I need to think about how to get to 25 pages.
Really? Because what? When we explain, you know, for the first time,
Didn't write what did you write down? I only have like the tables with the values. What, like, what did you write?
What?
Did you write notes? I didn't write
A little bit, not much, but it's just for like if I had to explain it to another student.
Yeah, I was kind of too lazy to get into that, you know, it's like programming, it's like interesting to do it, but then it's you know, to write another documentation. That's how I have been doing, yeah, I don't know. That's why I don't know if I would become an engineer.
Really?
Writing this expedition things. I just like the math.
But we want to do your life.
Sail.
Huh?
Sail.
Sail. Really? Great. I'm sailor. Want to say something? What project?